Hello, welcome. We're a little bit behind schedule, as I'm sure everybody knows. I also have a tendency to ramble and go over time, so I'm going to try and fight that tendency and see if I can keep this talk to some degree of schedule. So thanks for coming in. I'm going to chat with you today about hybrid cloud workloads, or at least I think I'm going to do that. I am Monty Taylor. I work for Hewlett-Packard. I'm a distinguished technologist there, and I work on OpenStack pretty much full-time. I also, just in case you aren't like, my Twitter followers or anything like that, and don't follow my every move, in which case you probably know more about what bands I listen to than any technology. I sit on the OpenStack Foundation board and also the OpenStack Technical Committee. So I pretty much just run around saying the word OpenStack and the word cloud over and over and over again. And people don't seem to not get tired of it. They keep wanting me to say the word cloud. So that's sort of a little bit about me. So cloud, OpenStack, cloud. This is sort of the thing we're doing. If you've been to any OpenStack events ever, you've seen this slide probably in everybody's slide deck. And one of the reasons for that is that some graphic designer made it, and I'm not a graphic designer, so I like to steal the work of people who actually have skills. You'll see a slide later on that is made by me, and you'll understand exactly why I want to take somebody else's slide describing what OpenStack is. But at its heart, I think even though it's marketing fluff, the slide kind of hits it at an important point, which is that OpenStack as open source cloud software is there to provide us with the compute network and storage that we like to talk about all the time, to be a layer between that and hardware. And then more importantly, the thing that I actually want to talk a little bit more about today is actually something that Mark said this morning. Sorry, we had 2 keynotes by Mark. We're going to have a panel later on today with 3 Marks. Apparently you have to be named Mark to do something around here. Mr. Shuttleworth's keynote earlier, he made the very excellent point that you don't really typically want a cloud just to have a cloud. You want to have a cloud to do something with it. You want to have a cloud for that box at the top there that says your applications. Your applications is actually kind of the whole point of this. I enjoy making making the joke that my mom likes to ask me if she can install OpenStack at home, if she can use this thing I work on, and I'm like, well, I mean, yes, physically you may download it and install it. It will be absolutely no good to you because you're a retired piano teacher, and so it's not really useful to her. But hopefully it's useful to those of us here who want to do things. And I want to point out a few things that are possibly a little bit different than what other people think. I think that rather than thinking of cloud as a way to get some VMs, to me a cloud is an abstraction layer. It's the infrastructure service. It's a way for me to interact with the infrastructural needs that I have in order to run my applications again, and it allows me to do that to Mark's point from this morning. If Google has or Facebook has 24,000 servers per engineer, then you need things to help you. If that was actually people physically interacting with each one of those computers, one person can't manage 24,000 machines. It just doesn't work that way. But with a cloud you can. And more to the point, you can certainly write cloud applications. In fact, everybody will tell you you've got to take a journey. You've got to rewrite all your applications to be for the cloud. And I actually think that's a bit full of crap. And I'm going to follow up on that in a second. But it's just a way for you to get computing resources. So you can do some really exciting elastic things with that. If you have, I don't know, if you're in the US and you're in advertising and you're going to have a Super Bowl commercial, that means that you're going to all of a sudden have a giant inflood into your website, and you've got to be able to handle that. And so this is sort of your traditional need for elastic applications. That's not the only thing you can do with cloud. You can do pretty much anything with cloud you can do with a computer. And so I'll talk about that a little bit more using one of my favorite examples, which is me, because I like talking about myself, and some of the things that I do with cloud, which will hopefully be really exciting for everybody. You saw this slide earlier today we basically just all steal slides from each other all the time. Again, a graphic designer person made this slide and I didn't, so it looks better than my version of this. So the thing that I want to talk about in the cloud application that I want to talk about is the CI developer infrastructure that we use to run the OpenStack project itself. We have a lot of it, and it is all itself a cloud application. So we use the cloud to help us develop OpenStack. And we do that, and there's the problem that we're trying to solve, right? Because, oh, great, I use the cloud to deploy things. Well, that's fine. If we've got 2,000 developers over the lifetime of the thing, and we've got 466 average monthly contributors, and we're merging 17,000 patches over a 6-month cycle, you can imagine that we might have some reasonably high compute needs that we've got to get out of something. We've got to be able to manage the collaboration between people from 355 companies, which if you haven't ever tried to help manage the collaboration between people from 355 companies, I highly recommend it. You're more than welcome to come work with us on doing the collaboration software. We welcome all types. So it starts with this. It starts with a piece of software called Gerrit. This is sort of at the center of everything that we do. And it's a standalone a piece of code review software. It's where all of our Git repos are, but more importantly, it enforces a code review workflow and allows us to enforce that. We do that because we have people from 355 companies all trying to work with each other, and if we just gave them all push access to repos, then there'd be all sorts of infighting, and I'm gonna go ahead and say that we probably wouldn't have grown to 2,000 developers, at least not this quickly. So we have to do that. The thing about Gerrit, and we run this in the cloud, right? This is because I don't have any computers to run the OpenStack project. I have 0 computers. I have a couple cloud accounts, but I have no computers. Gerrit is an enterprise Java application. I got to tell you, it's a giant pile of crap, as all enterprise Java applications are. And what I mean by that is it's designed to run in a single big machine, right? And so this is the thing that a lot of people have in their workplaces, right? You're like, oh, I can't move to cloud. I've got this giant JBoss application, and it has to sit there, and I've got to have an Oracle rack sitting next to it and whatnot. And that's great, and it helps us at HP sell you lots of really expensive hardware, and you should continue to buy it because it's good for me, I guess. It's probably good for you. But the thing is that this is exactly what this thing is. It's a monolithic thing. It can't scale out. You can't run it on more than one machine. So we run this in a Nova VM. We have its data file sitting on a Cinder volume, which is the block storage service in OpenStack, and we have the database that's behind it being managed by Trove, and all of these things are existing in the public cloud. For the first year and a half that we ran Gerrit, we actually just ran MySQL in the VM that the Gerrit instance was running in, and we just wrote local data to the local ephemeral drive of the server, and we did nothing special, and we backed it up. We had backups, but there was nothing cloud-ish about this application, and it is the central thing that is being hammered on by 2,000 developers all day long. There's still very little about it cloudish because it's not written, it's not designed. We'd have to rewrite it in order for it to be cloudish, right? So this is a little bit about, and I apologize for the small numbers over there. This is a graph of the usage events of our Gerrit server. We do all of our ops stuff in the public, so if you ever want to go dig into our graphite graphs, you're more than welcome to do it. Graphite.openstack.org. So this is one of the graphs. This is a couple of days. I think this is about 72 hours of usage, and it's showing. I can't even read it at this size. It's showing those peaks are about 900 code review events an hour. Down here at the bottom, you're seeing that people are uploading new change sets at the rate of somewhere between 25 and 50 an hour, and we're landing probably somewhere at about 10, 15 an hour there. So so what? A few things that follow from that are in a week we're merging about 250 to 500 changes. But that's just how many we merge. We test a lot more changes than that. Thank you. We get about 1,500 to 3,000 revisions of a change per week, right? So this is how many patches, how many revisions of a patch get uploaded into the system. And so this leads to about 10,000 new changes are proposed every 42 days. So it's a pretty active system. This is sort of where it gets into the cloud side of things. We test the ever-loving crap out of every change that gets proposed and every revision of every change that gets proposed. So for every one of those 1,500 to 3,000 change revisions per week, we do this. We run style tests on it. We run unit tests on it. We spin up a whole bunch of DevStack clouds, and inside each one of those DevStack clouds that we run Tempest against, we wind up spinning over the course of that run about 180 guests inside of the cloud that we spun up, which means that for every one of those proposed change sets, we spin up 5 to 10 DevStack clouds. We run about 10,000 integration tests across those clouds. And across all of those, it means that we wind up creating about 1,000 guests inside of the clouds that we've spun up to test the cloud software that we're developing. This produces about a gig of operational log data, just to give you an idea of sort of what's happening on every single one of those 1,500 to 3,000 changes that we're dealing with a week. So we have some scaling issues that we've got to deal with. So one of the ways that we deal with this is, well, we're writing open source cloud software, and a couple of the people that are really involved in this effort have public clouds that run OpenStack, namely HP, who I work for, and whose public cloud you should use, and also Rackspace, who are also great people. And we use their clouds to get the resources to do all of the testing that I just talked about there. So we wrote a piece of software called NodePool, and it's the least interestingly named piece of software that we have. I apologize for that. Normally we have fun names for things. But what NodePool does amazingly enough, if you can believe it from its name, is that it keeps a pool of nodes available and ready for testing. It does this actually in a multi-cloud manner, and I'll talk about that in a second. But this pool spans clouds, and it also watches the job queue. It watches the activity to anticipate the need that we're going to have. So this is sort of could not possibly, in the same way that Garrett could not possibly be more stereotypical enterprise monolithic Java application, this could not possibly be more stereotypical elastic cloud application. We spin up and tear down single-use throwaway nodes on demand. So this is actually a graph of our node pool from the same period of time that I showed you the last graph of the Garrett changes. And you can see that we're spiking up to, at one point in time in the various states that nodes can go through, we're using about 900 to 1,000 VMs at the top of these spikes. And then we get down into a point of about 200 sort of idle and ready to go things at the valleys here. So this is actually, you're looking at Thursday, Friday, Saturday. And you can tell that most of our OpenStack developers actually work for companies on OpenStack, and so we don't really see a lot of development activity that spurs the need for us to spin up and use clouds. So that's great. The problem with that is that now that we've got this completely elastic way to handle tests, we've actually got to be able to drive the tests in some way. And so we wrote this piece of software called Zool, which I'm not going to go into in too much detail, although I'm happy to talk for hours about it. But its job basically is to take that incoming pipeline, incoming fire hose of changes that are coming in, and the things that people are, the ways that they're code reviewing them, and all the activities that developers are doing, and make the decisions about what tests need to get run and on what results get returned back to the developers. This is again from the same period of time, and all this is these are graphs from a couple weeks ago. And here we're sort of seeing Zool requesting of the Elastic system that it do some things. The piece in the middle of this between NodePool to run the tests, or NodePool to actually be the place on which the tests are run, is we actually use, I'm sure most of you have heard of Jenkins. It's not particularly earth-shattering software. Pretty much everybody's using it these days. It turns out that at our scale, Jenkins falls over and turns into sort of a pile of mud. It is also a traditional enterprise Java application. It's not really particularly well suited for scale out because it has a single global queue. and it sort of has to sit on a single machine. It has slaves, yes. But the node pool thing that we've got there, what it's doing is actually creating slaves for Jenkins. We found that a Jenkins master can handle about 100 slaves concurrently. And when I say 100 slaves concurrently, I mean that in the way that we use it, we actually cause all 100 of those slaves to be running tests simultaneously. And there's some really bad global mutexes inside of Jenkins. So how do we scale that? How do we scale that enterprise Java application out with our cloud resources? I can't just do the node pool thing. I can't just have it be sort of this randomly elastically scalable thing, because it's a sort of standard thing. So in this case, we sort of took a hybrid approach, right? We wrote a plugin for Jenkins that sits in the front end and turns it into a worker in a Gearman bus. Gearman is a distributed job scheduling system that LiveJournal wrote back in the day for doing image manipulation and resizing. And it winds up being a great job bus. So our Jenkins master now talks to a Gearman bus, and our Zool, our piece of Zool orchestration software puts requests onto the Gearman bus, and one of the Jenkins masters picks it up. And I say one of the Jenkins masters because the way that we're dealing with this is actually a more traditional scale-out approach, not an elastic thing, but we actually have 8 Jenkins masters in our farm, and any one of them our node pool will attach slaves to as it creates them, and then whichever of them has the available resources to take a job off of the queue and run it, takes the job off of the queue and run it. So in this case, we modified a little bit. We didn't completely rewrite Jenkins, but we modified it to be able to work in a scale-out scenario. And that allows us to sort of bridge the gap between our elastic world and our fully elastic world and our very monolithic single point of failure. So I mentioned earlier that this is a multi-cloud situation. We have multiple public clouds and multiple regions in those multiple public clouds that we use that node pool presents us a single view of. So it creates nodes in all of them. There's a couple of reasons for this, but it largely comes down to failure. We have all of those developers doing all that at all times. If we were just in one cloud and it failed, everyone's work stops. Everything is done. And we wind up with something that's a little bit more akin to this, because the poor guys at Netflix only have one cloud that they get to use. And sometimes they're not able to stream you the movies that you want to watch because the fine folks in Washington State, in Seattle, sometimes things break. And that's fine. But in our world, we've got multiple vendors, multiple people running these things. It also, another reason that we have this be multi-cloud is that different of the clouds present different operational semantics. Some of them pick stability over speed. Some of them pick speed over stability. In this particular case, one of them runs Zen and one of them runs KVM. That actually doesn't help us at all, but it might be a thing that I might need to move things around. I might need to do bare metal testing. Because ultimately, there isn't just one configuration. There's a reason that Nova has 600 whatever configuration options that it's got, is that there are actually different valid configurations you might want that all sort of behave the same way. So we have, actually at this point, and I actually want to pause and say real quick, the HP branding and marketing people think it's important that I tell you that this slide does not indicate that HP is behind putting children into boxes. As much as that might seem fun from the slide. So basically don't just believe all the slides verbatim. So this is actually a breakout from the node pool graph that I was talking about earlier that shows each of those color lines is actually a different cloud region. And this spans 4 different clouds. So we've got HP's public cloud, we have Rackspace's public cloud, and then the OpenStack project itself actually runs 2 private clouds, effectively. We have a rack of hardware at HP that the community operates, and Red Hat has also donated a rack of hardware that the community operates. And as a team, the O group actually operates both of those, and those are also connected into the node pool. Why? Because we kind of need to be able to do some testing of some of the bare metal capabilities of the cloud. And I don't know if you've noticed this or not, but inside of a public cloud that's giving you VMs, it's very hard to test bare metal operational capabilities. Unless you are way more skilled than I am. So this gives us the ability to have a thing that looks like this. This is actually how we interact with it. It looks like one pool of resources, right? But what it actually is under the cover is this. And so we span clouds. A couple of weeks ago, Rackspace's DNS servers just stopped working in really weird ways. And we, of course, pinged them. We're like, hey, man, your DNS servers are broken. And they're like, oh, thanks, that's good to know. It didn't stop the OpenStack development because we also had nodes that were running in the HP zones. We've had the same thing happen in the opposite, where there's been an issue at HP and the Rackspace nodes allow us to continue to run. And this is one of the things that's really wonderful about the ecosystem of OpenStack and of OpenStack clouds is we've got now our business as you are, our application. The thing that matters to us is spread across multiple things, both public and private clouds, and we're running this in production right now. So if anybody's telling you like hybrid cloud is a thing of the future, we've been running a hybrid cloud for like a while now, and it works great. So you wind up, but I'm actually not really even talking about hybrid cloud as much as I'm talking about hybrid applications. The application that we're doing, the OpenStack developer infrastructure, it's got some monolithic pieces. Garrett and Zool themselves, even though we wrote Zool ourselves, it doesn't make any sense because it has to connect to Garrett for it to scale out. It doesn't have to. So they're both sort of just monolithic things. They're running in the cloud, but they're not particularly clouded. They're there. They're in a VM. They're in a machine. The machine looks like a computer. We have to back them up because sometimes computers fail. If they were on bare metal, sometimes computers fail. You still have to, take care of those aspects of it. We've got a set of scalable resources in the middle, which are a little bit more curatedly scaled out. When we need another Jenkins master, we spin up another Jenkins master, and we put it into the pool of things. Another thing that I didn't put on here because this is me making slides, by the way. You can tell the difference between me and the marketing people. We also have a scale out farm of Git replicas. We've got like 5 of them right now that sort of are behind a load balancer and serve out Git repositories. We don't need to scale that up and down like at whim. We need to do it once in a while, and we can plan for that. And then over on the right, we've got this node pool, which is actually doing elastic need demand based generation of cloud resources across four different distinct clouds, and presenting those back into the scalable thing, which is then connected into things. So this is one application. This is one workload, as it were, that's operating in the cloud in multiple different facets, and allows us to do that. And so ultimately, I hope it's sort of become clear from this. That the thing that's fascinating about cloud, the thing that's important in cloud, is the thing that was a really small box in that original slide. It's your applications. It's the thing you want to do, and what capability, and the fact that you actually get at your fingertips and behind an API all of the different types of things. You want some bare metal. You want some machines that are going to stick around for a long time. You want some ephemeral machines. It's all available to you, and it's all available to you in fact exactly the same way. We use the exact same tools to manage the elastic pool as we use to manage the static pool. And so ultimately, write a whole bunch of good applications that run on OpenStack. It'll be really great. And I'm actually at time, which is very, very exciting. So thank you very much.